Thank you, ma'am.
Yeah. So, how are you doing?
I'm fine. What about you?
I am also doing good. It's nice meeting you over here.
Yeah.
So, this is our ATAL FDP sponsored by the AICT,
Okay.
uh, which is a 6-day long online FDP in the evening hours for the academicians and the industry experts so that they can have the learning from your expertise. Right? So, can we start?
Yeah, sure.
Right. Ishika, you can please start.
Sure. Good evening, everyone. A warm welcome to day 5 of the 6-day online ATAL Faculty Development Program on vacuum technology in semiconductor manufacturing and packaging, innovations, applications, and challenges, organized by the North Cap University, Gurugram. As we advance further, we continue to explore the crucial role of vacuum technology and electronic design automation, EDA, in semiconductor manufacturing. Yesterday, on day 4, we had two engaging sessions on vacuum technology in packaging and etching processes under vacuum conditions.
In the first session, Professor D provided in-depth insights into vacuum-assisted packaging techniques, discussing how vacuum enhances reliability, precision, and durability in semiconductor devices. His expertise in 3D IC packaging, MEMS, and nanomicro reliability studies helped us gain a deeper understanding of the latest advancements in the field. Following that, Dr. C. Ramachandra led us through a fascinating session on etching processes under vacuum conditions, covering reactive ion etching, deep reactive ion etching, and chemical etching methods. His session gave us a clear perspective on how these processes contribute to high-performance semiconductor manufacturing.
As we move forward, today's sessions will take us into EDA for semiconductor manufacturing and vacuum measurement and control. Our expert speakers will explore how AI is revolutionizing EDA in VLSI design and provide valuable insights into vacuum measurement techniques and process optimization. Let's begin day 3 with enthusiasm and curiosity.
Our next session explores EDA in semiconductor manufacturing and its evolution with AI and machine learning. The integration of AI-driven automation in VLSI design is transforming chip development, improving efficiency, and optimizing manufacturing processes. We are honored to welcome Mr. Shubham Jain, CTO of EduLibrarian and former principal software engineer at Cadence Design System, Noida. With years of experience in EDA, machine learning applications in VLSI, and semiconductor processes optimization, he has played a key role in advancing AI-powered semiconductor design and verification methodologies. Let's welcome Mr. Shubham Jain to take the virtual stage and share his expertise with us.
So, thank you, Ayush, and thank you, Ishika, for this warm welcome.
Welcome, Shubham.
Thank you, ma'am.
You can take
Welcome,
it
sir.
forward.
Yep. Thank you. So, yeah, one thing which I think they both missed was I graduated from ITM itself. So basically, I am a product of ITM, former ITM, when it was under MDU. So now it is a university in its own. So it feels proud to come back to alma mater.
Yeah.
So
We are also proud of you.
thank you.
So you are leading an example for Ishika and Ayush. They will be they
So
will be setting this that yeah, Shubham was we have
yeah,
met them.
they are from
So
CS department, I guess, right?
they both are from CS
Yes.
department.
Yeah,
Yeah.
yeah.
So you can take over, Shubham.
Yeah, I am sharing my screen. Let me know if my screen is visible.
Yeah, it's visible
So it's
now.
visible.
You must be able to see the presentation, right?
Yeah, we are able to see.
Yeah. So in the interest of bandwidth, let me switch off my camera.
Yeah, no worries.
So yeah. So basically, today what we are going to discuss is how AI is revolutionizing VLSI and EDA domains. So basically, they both go hand in hand, and EDA is a pretty niche department which is less known, and even less known to CS people. So yeah, I have around 11 years of experience, and I started in 2013 with Cadence Design System. And in between a short while, I also went to Siemens EDA department, which was formerly Mentor Graphics. So then I have now recently started my own venture. So yeah, starting the presentation, which is the first slide for this presentation is how the VLSI and EDA tools, how did they evolve together? So basically, before EDA tools were there used to be a lot of manual process, which obviously would result in increased time to market. So initially, a lot of manual stuff would be done to draw the schematics, to find the DRCs in the layout design, to design the for, in physical design also there was a lot of manual stuff. In design capturing there was a lot of manual stuff. So since the inception of EDA, companies have given a lot of uh, value to this EDA domain. There are a lot of EDA companies in the market, but now now they're handful after a lot of M&As. So there were initially a lot of companies. Now I think there is one Cadence, Synopsys, Siemens, which was Mentor Graphics, and there is one Altium. So again, there are a lot of M&As going on. So yeah, so it is a pretty niche domain, and very few companies play in this domain. So since its inception, EDA companies have given a lot of breakthrough technologies, ranging from spice simulators, logic synthesis, and physical design automation. Now, as everyone knows, there are challenges introduced by Moore's law, which states that the number of transistors in a chip would keep on doubling every 2 years. So this is a lot of this gives us as a EDA engineer a lot of brainstorming sessions, a lot of blackboard sessions to come up with innovative solutions to basically have a performance optimized softwares for product manufacturers like Apple, Samsung, all the product companies that are available in the market. So they all use EDA tools behind the scenes. So this slide would give you a broad view of.
Shubham, side lights are not moving.
Oh, is it?
Yeah,
Which slide are you able to see now?
third slide.
AI use cases.
Yes, yes.
Okay. Yeah.
Maybe you can put it in a presentation mode, so it will be once you as you are moving, it will be visible.
Okay. Hold on. Let me share my whole screen.
Yes, yes.
Now I guess it should be fine.
Yeah, now it's fine. Yes.
Yeah. So I think you people missed this slide, right?
We missed the earlier slide. Yeah.
Okay. Okay. So yeah. So basically, what I
Hmm.
was explaining was how the EDA and VLSI go together hand in hand, and how the evolution took place. So initially, there were a lot of manual steps, and now the EDA companies have automated quite a few of those steps and basically reduce the time to market for every product that product companies manufactures. And a lot of breakthroughs given by EDA companies like spice simulators. In logic synthesis, they have given a lot of breakthroughs. And recently, with the advent of AI, a lot of tools of cadence like Genus, Innovus, Virtuoso, they have given a lot of breakthrough performance optimizations to our product companies. Coming to this slide, this slide basically gives a broad overview of what AI has in its store for semiconductor industry. So ranging from supply risk management to inventory optimization to visual inspection of wafers. So basically, if I go a deep dive into visual inspection of wafers, so but what basically this would mean is we would take a lot of snapshots of the already uh, defect already wafers which have defects in them. So we would take a lot of visual snapshots of them, and on top of it we would inject a lot of uh, uh, new images which are built on top of those earlier images, and give and train those all images using basically neural network. So basically what we use is AWS. Nowadays it is quite popular. So basically we would take a lot of images and train it. So there are different models out. YOLO, you can use YOLO. There are all there are much further. Basically YOLO is the one that I've currently used. So when you have a trained model out of it, what you can do is, if you have a new wafer, you can take the snapshot of that new wafer and give it to the model, and it will tell you whether the wafer is defected or not. So this basically removes the manual intervention in the process. So there would be some kind of validation step which is manual, but yeah, the complete step has removed a lot of manual intervention. The next use case would be chip design and development, which I would come up in further slides. Next is procurement and material planning, predictive maintenance, sales and marketing transformation. So basically, the current venture that I've started is a kind of a thread which goes along all these steps. Next is why do we need AI in EDA? So basically, again, there is a Moore's law that I've stated before. Due to that Moore's law, there are tight deadlines for our customers to meet. So those customers come back to us that we need an efficient process, and that's how this cycle starts. And again, another point which is of importance, why we need why we need AI in EDA is conflicting PPA goals. There are scenarios where a person who is working on PPA tends to uh, do a bad job, not a bad job, but yeah, tends to uh, do a less analysis of power and performance. But with the AI enabled EDA tools, the product companies can uh, do a starting step with AI enabled tools, and then have a human intervention step. So basically what AI does is, it always does a starting job for you, and then you can take it from there on and do all your manual stuff that you want to. So basically it gives you the initial boost into the system. AI predicts outcomes and automates tasks. It obviously reduces human errors because of data driven learning. So every AI step involves data in it. You train your models on data. That's how you develop the AI models, and you take it you then take it from there on, and inject new images into that model and retrain it step by step. The techniques that are being used currently in our EDA domains for AI are machine learning, deep learning, reinforcement learning, and the most recent technology that we have been using is generative AI. Generative AI has basically uh, is a complete breakthrough in the market. Now coming to the key applications of AI in EDA. So different areas which has used AI are design space exploration, placement and routing. I will come to this step in next slide. Placement and routing. Then in logic synthesis also. Then again in verification, power optimization, fault prediction. So yeah, fault prediction. The example that I just spoke about of wafer comes into this category of fault prediction. So basically at different levels there are different fault predictions. So if we talk about schematic and layout, the fault prediction would boil down to fixing the DRCs. In physical design it would come back to having the technology files from the foundries and fix your designs upfront. Next is generative design for custom circuits and autonomous chip design. So yeah, these are the few examples of the companies that uh, that yeah, these are the few companies that have heavily invested in AI. Cadence, I was part of. Synopsys, I know of, they're working in this domain. Google, as you all know, is heavily invested in AI, has given a lot of generative AI models to us. And NVIDIA is a company which basically is the backbone of every product company. So coming to place and route. So basically, how we have used AI in placement and routing technology. So basically, what we do is so basically a problem came to us that in a layouting stage, you the customer has to basically place all the components such that there the PPA is perfectly met. If not perfectly, there is a very nice trade-off between them. So basically, how we solved this problem was uh, the schematic that a user develops it using manually. The schematics in the today's world are being developed manually by a CAD engineer. So basically, when he or she develops the schematic, we kind of tends to take that intent into the layout. We take that schematic intent into the layout, and then we do the placement, keeping in mind the PPA. So this process is very computational intensive, and mind you, AI is very computational intensive job. Now after this Nvidia and all the chips that AI that Nvidia has developed, uh, even though they are taking less time, but they are computational intensive. So basically what we do in place and route is we take the schematic intent of the design and the place the layout such that the parameters for tuning the model are met. Now brief light into what I am currently doing. So basically chip manufacturers provide their chip functionality in form of data sheets. So whether we talk about TI, whether we talk about ADI, Infineon, Diode Technologies, there are a number of companies that develop numerous parts, whether be it from audio department, whether be it from data converter department, or capacitors or regulators. Every chip company gives a data sheet along with their product. So that data sheet serves as a golden source of truth for all the engineers up the ladder. Feel free to come in at any point. if you if you do not understand anything, we would like to have this session interactive, so feel free to come in at any time. So data sheets are a golden source of truth for every engineer up the ladder. So now what we can do is we can leverage different AI techniques to create models which are used further up the ladder. So when I say models, what we can do is, using AI techniques, we can develop spice models, we can develop ibis models, verilog, vhdl models, using AI techniques which can be used by engineers up the ladder. So this kind of is a breakthrough wherein lot of manual stuff that goes into building libraries would vanish in few coming years. Now this slide talks about VLSI development cycle with AI enabled EDA. So at the center you can see, uh, so basically this is a design cycle of a product, and basically AI is in the center, which fits in all these domains. In design rule checking also AI is used. In ATPG, so basically uh, AI is used to basically take it takes in the design as input and outputs a best fit ATPG pattern which can find out defects very upfront. So that's how AI is being helping ATPG department. Now again, design for manufacturing uses AI. Design exploration. So basically what I mean by this design exploration using AI is, uh, so basically it basically traverses all the tracks in a maze. So let's say you take an example of a maze, and there is a cheese in there's a cheese in one corner, and a rat wants to find the cheese, and there are all the different ways. So now manually what a user would do is, user would take one path, and when he would get stuck in that path, he or she would take another path. So that's how manual stuff works. Now with AI, a lot of multiple, it's like a multi-threaded it's like a multi-threaded way of traversing the maze. So design exploration is a very perfect fit domain for AI, wherein uh, wherein a design wherein a user, so basically what I mean by this is, I have a design, a requirement in place, and I tell the AI tool that give me all the possible scenarios of this product, and I can then find the best fit uh, using manual intervention. Next important point is RTL design optimization, and then is physical design optimization. All these cycle is being driven by AI. Now this is a typical flow wherein we get an H spice netlist along with statistical. So basically this netlist has statistical variation. It takes in PDK files, and there are standard cell descriptions which are being input in this netlist file, which is being fed to the simulator. And after the simulator, we get PVT aware circuit simulations, and and this is where AI comes in. So basically, what we do over here is we take this data in, and and basically the main requirement of this step is to get the statistical aware circuit performance evaluation. So basically what we do is we have unseen statistical variation. Now we train the model by tuning various hyperparameters, like what is the batch size, how much training cycle we want to do. These are the few hyperparameters, one of the few of the lot of hyperparameters that we train on, and finally come up with the AI model, which would take as input the unseen statistical variation and output the statistically aware performance evaluation of the product. Now, this is a typical flow, typical design flow, which has design, and along with this flow, we also have different tools in the market which are belonging to this domain. This is basically the front end part of the design, and these are typically the back end design flows. So initially we have design specification, then we have architectural design, then we have behavioral level design and verification, where the Verilog and system Verilog stuff comes in. Cadence has Virtuoso, Synopsys has VCS, and Siemens, which was earlier known as Mentor Graphics, has Model Sim for this. After this step, we have net listing, then formal verification, and followed by floor planning, routing, static timing analysis is being done in this clock tree synthesis domain. Next, we have layout, and in layouting, what we do is typically DRCs, uh, layout versus schematic comparison, and ERCs. So basically, this step has a lot of value when it comes to AI, since we have a lot of data in this layouting domain. So DRCs, LVS, and ERCs are being typically now being done using AI, and Cadence basically markets its tools like Innovus and Genus with a performance gain of 20x to 30x using AI. And this is the final fabrication process. So before this final fabrication process, what we have is technology files from the foundries, which go back to the physical design stage, and at this, again, this physical design stage, we find the errors, if any, using those technology files. So a lot of AI stuff can be done in that domain as well, wherein the input to the tool can be the technology file, and output could be the errors in the design process. Like I said in few slides before, that data is the most important part for AI to be successful in this era. The concepts of this AI existed in 90s as well, but at that time we did not have compute power at our disposal, and nor did we have a lot of data at that time. So these are the few stages which have a lot of data inside it. Fabrication. So this has data to ensure defect-free and defect-free transistor level fabrication. At the wafer test level, this has pre-assembly data to drive specification compliance. Then is final test, which has post-assembly data. Then is assembly inspection, which has final data analysis to capture defects before product is shipped out. System testing. This basically has data to ensure system with different semiconductor products, so that different semiconductor products work together. And finally, the miscellaneous, where a lot of other stages in the design flow can kick in. So once we have AI in EDA domain, EDA companies can now target different industries because they have AI at their disposal. They used to initially target, and quite for a and for quite a long time, they are being targeting this semiconductor and electronic manufacturing domain, which with the help of AI, the product companies can now basically develop high performance CPUs and GPUs, just like Nvidia is one of our customers. uh, power efficient chips for IoT devices can also be built now. In automotive domain, this is a pretty new domain, and pretty fast driven domain. Like with the advent of companies like Tesla, this domain is growing like hell. So with a shift towards ADAS is a new technology that in India also it has now started. There are cars, if I'm not wrong, Mahindra has come up with few cars which has ADAS in it. So with this new technologies, AI is all the more needed in EDA domain, because uh, there are chips with safety critical features for real time decision making are also required here. In the healthcare and biotechnology domain also, EDA companies can now target, because a lot of imaging stuff goes behind in this healthcare domain. So there are various scenarios wherein we have a snapshot of an x-ray of a chest x-ray, of a CT scan, and the AI tools can say that whether the x-ray is perfect, whether there is a fracture or not. So in healthcare domain also, EDA is now proliferating itself. And again, IoT is a niche department which has gained a lot of significance, because automotive has gained a lot of traction in the market. So a lot of smart sensors, industrial IoT systems are now being built on top of by using our EDA tools. So this is basically a typical growth of AI in semiconductor market. This is a perceived growth which would reach around 232 uh, billion in 2034. So this is perceived to be reaching around 230 billion market in 2034, and it is currently at 65 billion market. So it has a lot of potential in it, and there are a lot of engineers which we would require in EDA domain to help us out. And software industry will grow at this same pace, and along with the product companies. So VLSI and EDA would always go hand in hand. VLSI cannot run independently, and EDA cannot run independently without VLSI. Now the point where industry and academic collaboration can happen. So there are a lot of research opportunities in AI driven physical design, like I explained before, and hybrid ML techniques. So there was a point where I explained that in physical design step, uh, when the design is being designed, when the design is being finally basically is ready to to be sent to fabricators, to fab labs, we get technology files from that fab houses. TSMC has its own TSMC has its own technology file. So basically that means that at what nanometer size they are developing a chip. So before we send the final GDS file to the fab houses, we take in this technology file and find the errors in our existing physical design. So at this step there is a lot of AI potential in it, and we are working in this domain. Companies like Cadence and Synopsys are working in this domain to basically help the design engineers use this AI stuff and come up with those errors very quickly, and basically reducing the time to market. So basically what academic people can do is uh, encourage combining software engineering, electronics, and data science. So basically, we can have multidisciplinary course wherein we have software engineering, electronics, and data science merger. So basically, when I did my CS, I went outside ITM and did a Verilog course to basically get ready for this EDA domain. So in the similar manner, academic can basically have a multidisciplinary course, and I am sure there are some efforts being done in this area. Basically, so yeah, so this is where academic can pitch in, and there are a lot of research opportunities in this area. Now coming to the challenges that we currently have in this AI era. First is data availability and diversity issues. So what happens is every product company thinks that they are developing something crazy out there, but not always it is true. But they think they are developing something crazy, and that is why they tend to not give us data that we require for our training process. So there are a lot of data availability issues in the EDA domain, wherein we kind of go to a product company and say that we are ready to sign NDAs with you, but still we do not get we so basically, like for an example, if iPhone, if latest iPhone is 15 or 16, they would give us a design of iPhone 4 or 5, or at max iPhone 8, and not further than that. So that basically hinders our technology, because we do not get the same kind of density of design that is now in the iPhone 16. So Moore's law is like so basically Moore's law says that the number of transistors in a chip would double up every 2 years. So if a company is giving us a design 5 to 10 years back, that is not going to help us out much. It helps us out, but not in a great manner. So yeah, data availability issues are a key is one of the key issues that every EDA engineer talks about in today's world. As I said before, there is a high computational complexity and scaling concerns. So, when we train an AI model, there is a lot of carbon emission being done, so which is of concern to our environment. So yeah, with AI in place, there is high computational complexity which can be expected from this domain, and scalability concerns is obvious. Now, next point is black box nature of AI models. So as I basically talked about YOLO models. So basically, YOLO is a kind of a black box model which gives us a functionality of taking in a few lot of images that you currently have, and outputting a model, a trained model on that image, so that the YOLO in between is a black box for AI engineers, unless and until you are developing your own your own training model. The lot of engineers in the market today are using those YOLO models and training their models on their own image dataset. So yes, there is a lot of black box thing in between, which kind of has to become gray if not white. So this black box has to somehow become gray, so that we can tweak certain parameters in those models. And of course, there are integration challenges in the workflows. So basically, what I mean by this is EDA tools the currently that we have are initially they were initially a lot of algorithmic based, and now since the AI has come up, uh, we need a lot of people to basically integrate those AI models with the existing EDA tools. Now coming to the future trends in AI driven EDA: autonomous chip design. So this I want to keep it open. So what do you people think? Can there be an era wherein you give a specification of let's say a phone or a laptop in a simple English, and you with after using the AI tool, you get a lot of designs, and you can finally select which one is better for you. What do you think? Will that stage come up in near future?
You can write in the chat box. The replies are yes.
Oh, nice. So we have a lot of good. So are students also in this session?
Very few, I would say.
Okay, okay. So I must say that the faculty members are basically uh, doing a great job and doing a lot of reading stuff, because this would be a near future. This will be a reality in coming years with generative AI in place. So yes. So next question to you people is integration of yeah. So basically, how can we integrate EDA advancements into academic teaching? So basically, this point I wanted to throw for a larger audience. If some mics can be switched on, or because I'm not able to read the answers what you people say.
Yeah, those who want to give the answer, they can raise their hands. We will unmute them. If anyone knows the answer, please raise your hand. Yeah, there is.
There is no one answer. This is just an open question that basically how can we incorporate AI EDA advancements into academic teaching?
Yeah,
According to
one.
me, yes, we can do. If there will be AI in teaching, it will be very easy. It will very easy to analyze every student's performance, and we can customize their we can customize their styles and what to teach them. Also, we also the teachers or the faculty would be that it will be very easy for the faculty to identify like what are the weaker areas for that child, and what new strategies the teachers should also apply in their teaching.
Yeah. Thanks for giving this. So basically, this is a completely uh, innovative idea of taking this domain into academic teaching. So yeah, so great answer. I would require some more answers to pitch in.
One of the answer is by using the open source tools.
Oh, nice, great. Again,
Yeah, more innovative ideas are required. You can please raise your hands.
so during our days when we were studying, we used to go to a lot of EC professors. I used to go to Sharda ma'am. I used to go to Naveen sir. And there was and there is, I think, one sir, Neeraj Shukla sir, right? He used
Yeah,
to
he
be
was
there
there.
in.
Yeah, he was there, but now he's not more associated with the North Cap.
Oh, is it? Okay,
Yeah.
okay, okay. I think if I'm not wrong, he has gone abroad somewhere.
Yes, yes.
Yeah. So yeah, so there were a lot of, so once I did my Verilog course, I used to go to a lot of professors to teach us more Verilog. And then we kind of developed UART model for this for ourselves. So yeah,
One more answer has come: integrating 3D modeling into teaching complex concepts.
okay. So
Rama Shankarji has mentioned AI is open tools by which we solve problems easily in short time.
yeah. Can you can you please throw light on this 3D thing? Uh, this is a
We
great
can
this is a great
unmute
solution.
unmute the Harshvardhan. Harshvardhan, you can please raise your hand. Yes. Yes, Harshvardhan, you can unmute yourself and share your views. Is it so? Let me make you a presenter. I hope it will be. Are you able to now?
Yes, ma'am.
Yeah,
So
please.
basically, 3D modeling can be used to teach complex concepts like molecular structures, geological formations, and even some scientific discoveries on like moon, if you say.
Oh, right. Got it. Got your point. Awesome.
Okay, one more is there.
Also, according to me, we should apply gamification in the in the education sector also, if we are talking about just education, because students in the today's world want something easy to study, and the gamification or the simulation process would be very easy to grasp new things.
Awesome. So basically, we can come up with EDA tools which kind of uh, are a sort of a gaming, which has some sort of gaming methodology in behind it. Got it.
Yes, yes.
Awesome thinking. So yeah, so I have one or two more slides. Am I the presenter now?
Each sheet was divided into number. Yes, you are presenter.
Yes, you are the
We-
presenter, Shubham.
Okay.
Yes, yes.
Yeah. So yeah, next slide talks about encouraging research and collaboration between academic and industry. So there can be a lot of focus on academic research on short term and long term goals. So short term goals would mean teaching AI courses to students, to EC students as well, because the lot of stuff that are being done in the market is a kind of mixture of EC and CS. So yeah, so EC people have to come up with some courses, have to go for some courses which require AI, which give them those which give them those AI advancements. And CS people would have to pitch in and come up with and go for some courses which have VLSI design in it. So yeah, again, multidisciplinary is the way to go for our academic domain. And we can promote collaboration through industry funded labs, uh, joint PhD programs, and internships. So yeah, I'm sure this is being currently done as well. So yeah, North Cap University has been a leader in giving multidisciplinary courses to its students. Their faculty members work tirelessly day in day out to basically make those highly valuable engineers in the market. I am myself a product of NCU. So yeah, I can say by my example and few other friends of mine. Uh, yes, so NCU definitely is a step up when it comes to private education in our country. So finally, as I said in a lot of my slides, that AI is redefining EDA and VLSI design with transformative potential. It is reducing time to market like anything, because every day you kind of get new phones. Every year you kind of get new phones. Samsung is uh, working on new display technologies. iPhone is coming up with new watches. Apple is coming up with new watches. So there is a lot of r&d that goes in behind the scenes, and a lot of those r&d is being done on these EDA tools. Academic plays a vital role in driving innovation and preparing engineers. And uh, yes, we should encourage curiosity and optimism for the future of AI in EDA. So yeah, so we can come up with questions if I think a lot of people must be having, a lot of faculty must be having. We can come up with a lot of questions now.
Yeah, there is one hand raise. Yeah, please, you can ask Bhavanari.
Maybe
Thank you,
if
ma'am.
yeah.
Thank you, Mr. Shubham, for the wonderful presentation on AI for EDA tools. Like my general
Hello.
Your voice is lost.
yeah, right now, yes.
Yeah, you're audible now.
Yes. Thanks for a very nice presentation on EDA, AI for EDA tools. My question is like, I have two questions. One is like, recently I have read like, right now we have a customized chips like ASIC.
Yes.
So they also, a chip can also, a AI-driven chip, which is manufactured, can also be altered the internal contacts, like how it is done in FPGA kits. This
Can
is
you can you
number
come up?
one. I have read.
Can you come up again? So basically, what you are
We have
saying
a
about?
ASIC.
Yeah.
We have
Go ahead.
ASIC design. We have an ASIC design, right? So they
Yes.
are customized. So AI-based ASIC chips can be ASIC can be modified according to the our design more effectively, like FPGA. I've
Okay.
read
So
one.
basically, so basically, what you are trying to say is, how is ASICs? How can we use AI in ASICs to uh, give a product like FPGAs? Is it?
Yes, yes.
Yeah.
And also another question is like FPGA kits. When we have the restrictions in the number of input bits for in FPGA kits, because we have various models of FPGA where we can give 16 overall number of inputs will be 16, 32 like that.
Right.
So
Right.
in this case, when we apply AI for the same, would there be revolution in applications of FPGA kits?
So I can answer your initial first question, which was targeting around ASIC. So basically, what we can typically do is, uh, since ASIC is a specific customized chip, what we can do to give it a functionality of an FPGA is, we kind of can connect it to a server which has an AI model trained residing on that server, and then based on the input, we kind of tweak that AI model on that server and give the output which is analogous to what FPGA gives. So this require basically a server. This will require basically a model which is residing on a server and a communication between that ASIC chip and that server.
Thank you.
And regarding that FPGA kits, the number of bits issue, I don't think that I may not be knowing it, but what my guess is, uh, AI won't be able to help you out in giving more number of inputs to the FPGA kit. That's my initial guess. I will take this question up and I will reply to either Anu ma'am or Pooja ma'am. I will reply to this question.
Thank you very much.
Yeah, the next question you can ask Rama Shankar.
Good evening, sir. Thank you very much.
Yeah, good evening, sir. I should say, sir, you please do not say me, sir. I am your student.
I am also a student, sir.
Oh, is it?
My
We
question
all
is
are
very simple,
learning.
sir.
No, ma'am.
Uh,
You all are basically my gurus. So it is very awkward to hear,
Only
sir.
I want to suggestion, sir.
Yeah.
Uh, how AI predicts semiconductor wafer defects before fabrication, sir?
Can you come up again?
How AI predicts semiconductor wafer defects before
Okay.
fabrication?
Okay. Got it. It will not basically what we do is uh, after fabrication. So
Yes.
it is a kind of a loop. So
Uh,
what?
uh, Before fabrication. Before fabrication.
Yeah. Got it. Understood your question. So basically, what we kind of do here is we kind of get lot of wafers
Hmm.
after fabrication, of
Hmm.
which we take snapshots.
Hmm.
Okay. Now
Hmm.
those snapshots become our golden truth, and during before the fabrication step, we kind of compare our image that we so basically we train model a lot of images we have. So there are a lot of images that we have of those wafers, and we kind of train the AI model on those images and use that AI model to predict if this wafer if this chip is having some defect or not. Did I answer it? Hello.
Yeah, Shubham, I
Uh,
think.
I satisfied, sir. Thank you very much.
Did I answer the question, sir?
Yes, sir. Yes, sir. Thank you
Thank you.
very much,
Thank you.
Subhan, sir. I'm
Yeah.
satisfied to you.
Thank you. Thank you.
Hello.
Yeah.
So basically, my question is, like we are going to completely rely on that AI-driven automation in the chip design. Like you are in this industry, and maybe in the next decade, the AI will completely take over that chip designing. And according to all of us, human intelligence is always greater than artificial intelligence. And whenever the topic of AI comes in the market, always the crowd has first question: will AI take over the jobs for the jobs of the humans? So is it very okay to rely on completely to the AI for the chip designing, or some
So
kind of human intelligence will also be necessary in that field?
so this was my initial, or I think third or fourth point that I made in the presentation, that a human effort can never be underestimated, but what can be done using AI is the initial effort minimization of a human. Like, for example, if I talk about the domain which I am currently working on, a user takes in a datasheet and develops a library of models, a spice model, ibis model, basically verilog model, vhdl model. They kind of develop it reading datasheets. So what we are saying is, we can be of help to you when we give you the initial model from the datasheet. Now you take it from there on. एक सो बेसिकली हमने आपको एक हेड स्टार्ट दे दिया. हेड स्टार्ट देने के बाद आप उसमें एरर्स खुद फिक्स करके इसको आगे बढ़ा दीजिए. दिस इज व्हाट एआई विल डू in the near future. It cannot take away the human job. So yeah, so let me correct myself a little bit here. The initial coding job that a software engineer does will go away, but yes, the engineer which takes in AI input and then uses his or her brain to take that output further will remain valuable to this industry. Just like this is just an analogy. When computer came in, when computers came in, and all the more when they were affordable. Technology is useful only when it is affordable. So when computers came in, there was a buzzword that computer would take away the jobs, and see what it did. It created all the more jobs. So yeah, AI will take away only a few jobs which are redundant in today's market, but it will create a lot of further jobs, a lot of further paradigms. It will give a complete paradigm shift to this VLSI domain and EDA domain.
Also, I have one more question. Like, if we are going to rely on AI for the making of chips designing, so like the advanced computing will be very easy as AI is doing it. So will the cost of that chip development would be less in the future?
Yes, that is exactly what AI would do. Likewise, when you so initially Nvidia gave its chip Blackwell. You must have read about it, right?
Yes, yes.
Yeah, so Nvidia gave this chip Blackwell and said that it is highly compute. It has a lot of compute power inside it, because till then DeepSeek did not come in. With advent of DeepSeek, what we are seeing nowadays is a normal laptop can also do, if not now, in near future, a normal laptop will also be able to do a training job. So that will effectively bring down the production cost of a chip and of a product in the market. Yeah, but that was a good
Okay.
question, Sridhar.
Okay. Thank you.
Any more questions?
There are no questions in the chat box.
Okay. If anyone is having any question, you can raise the hand. I think no more questions, Shubham. Thank
Okay.
you so much for
So did
taking
I
out
do
your
did
time
I
in the
did
late
I do
evening.
that badly?
Yeah?
Did I do that badly that there are no more
Arey,
questions?
no, not at all. The session was too good, I would say, and highlighting more about the AI and the ETA tools. I hope even the Ishika and the Ayush, our CSA students who are sitting here coordinating this event, they might have got the thing, but the glimpse of it. But we are
Yes.
going to, yeah, the
Yeah.
session was very well planned and well prepared, I would say, very informative. Thank you so much for taking out your time. I
Thanks a
would
lot,
say.
ma'am.
And We are
I'm
getting in
always.
the chat box. That session was very informative. People have started writing.
Thank you. Thanks a lot. It is always my pleasure to come to this university again and again. I recently gave a small talk. I think that was, I think, 1 or 2 years back. Vandana ma'am basically
Okay,
coordinated that
okay.
talk.
Okay, okay, okay. Right, right. Thank you. I think Ishika, you can take it forward. You are muted.
Thank you, sir, for an enlightening session on revolutionizing VLSI design using AI in EDA. Your insights have deepened our understanding of how EDA is shaping the future of semiconductor manufacturing. We truly appreciate your expertise and the valuable knowledge you have shared with us today. Thank you so much, sir.
My
Thank you
pleasure.
so much, Shubham. And I
Thank you
would,
so much, sir, for inspiring us.
yes, and taking out the time, the late evening after the office hours.
No problem. It's Friday.
Yeah, I know that too, Friday evening.
Fridays are good for us. We have kind of 2 days gap.
Okay, okay, that's good. That's good. So we are having our next resource person also here. So thank you so much, Shubham. Once again, we
Thank
can,
you, ma'am. Thank you.
yeah, thank you, everyone. So, Vinay sir, Dr. Vinay Budraja is here.
Hello everyone. So I hope that you all can see me.
Yeah, we can see you. How are you?
Yeah. I'm doing good. How about you? So overall, the conference going really very well and very informative. Shubham, very nice talk. So
Yes. Yeah, we are. I hope it is an early morning there.
yes, it's an yeah, early
It's
morning.
an early morning. We are starting your day.
Yes, yeah. At least like because of this event, I came early to the office.
Yes, yes. Thank you so much, Dr. Vinay, for taking out the time and coming to office. I think it's around 6 a.m. or what is the
No,
time
no, it's
there?
7:30 a.m. 7:30 a.m.
7:30
Actually,
a.m.
it's
Okay.
different time zone, different place states.
Yes, yes,
So it's
within
I'm in the central time zone, so it's like 7:39 a.m.
7:39. That's too early. You have moved to your office.
Yeah, but that's okay. I wake up early, so it's good that I reach office early as well.
Thank you. Thank you so much, Dr. Vinay. And it will be our pleasure to listen you. We are waiting.
Yeah. No,
Yeah.
I would like to thanks to all of you to the organizing committee. You invited me for the talk, so it's really an honor and thanks for giving me the opportunity.
Yeah. So I would like to mention to the participants that Dr. Vinay is working as a professor in the Northern Illinois University in US. So he's an expertise. He will be taking us through the clean room facilities, the vacuum facilities which are available in the Northern Illinois University, and maybe in future we can all work together, right? So Ishika,
Yes.
I would like to take it forward.
Sure, ma'am. Our next session shifts focus back to vacuum technology, specifically on vacuum measurement and control, which plays a critical role in semiconductor manufacturing and research. We are delighted to welcome Dr. Vinay, Assistant Professor, Department of Electrical Engineering, Northern Illinois University, USA. With a strong background in vacuum measurement techniques and process control, he has significantly contributed to improving vacuum stability, pressure monitoring, and real-time system control in semiconductor fabrication. Additionally, Dr. Vinay's session will cover vacuum pump in detail. Sir's expertise in vacuum metrology and system optimization will provide invaluable knowledge to researchers and professionals. Without further ado, let's welcome Sir to take the virtual stage. Sir, the stage is all yours.
Yeah. Thank you,
Welcome once
Ishika.
again,
Thanks
Dr.
for
Vinay.
that
Yeah.
nice. Yeah. Thank you. Thanks, Ishika. So should I turn off my video to get more bandwidth or
Yeah, you can, please. Yeah.
and you guys can see my screen, right?
Yeah, we are able to see your
Yeah.
screen. You can, if required, you can turn into the presentation mode.
Okay. Yeah. So yeah, please, Ishika, please stop me in between if anytime the connection is lost or you guys are not able to see my screen.
Sure, sir.
So, okay, so hello everyone. I would say good evening, everyone. My name is Vinay Budraja, and currently I am assistant professor at Northern Illinois University. First, I would like to thanks to the organizing committee to invite me for this presentation. And currently, I am working at MRDL. So this is Microelectronics Research and Development Lab. So we have clean room facility over here. We have three type of clean rooms: class 100, class 1000, class 10,000, and you know the basic definition of class 100, 1000, 10,000 is like that the dust count within per cubic feet, right? So 100 dust count per cubic feet, 1000 is 1000 per cubic feet, and 10,000, 10,000 per cubic feet. So we have three different areas, up to 2,500 square feet of class 100, 1750 for class 1000, and 950 of class 10,000. And okay, in the Google, you can search from if you type MRDL NIU, you can find the details. And we are equipped with all the required equipments and processes for the semiconductor device fabrication and characterization. And we have hybrid microelectronics lab, thin film lab, semiconductor lab, photo plotter, photo mask analysis lab. In the hybrid microelectronics lab, we have the tools such as the Keithley high temperature, low temperature, and at room temperature, CV, and the high frequency measurements. Thin film lab consists of the processing equipments such as sputtering, thermal evaporation, and photolithography, e-beam sputtering, e-beam evaporation, and magnetron sputtering. Semiconductor lab has some more tools for the measurement, material characterization, such as SEM and ellipsometer. Photoplotter consists of the photolithography processes, and we can produce the mask and perform the photolithography process. Uh, we have a screen printer and inkjet printer as well. So we can produce mask for screen printing process, and inkjet printing is the maskless technique. Analysis lab has some more supplies for the characterization and electrical testing. Here are the main outlines of my presentation. So first, I will start from vacuum system technology, explain what is the vacuum system and what its use in device fabrication and characterization. Role of vacuum in semiconductor processes. So how vacuum play a role in the semiconductor device fabrication. Importance of vacuum in semiconductor manufacturing. This will cover the importance, why vacuum is so important in semiconductor manufacturing, and without vacuum, we cannot consider any chip fabrication. Control of vacuum lines in semiconductor manufacturing. So this will cover the main vacuum lines, with how it's different when you work in a in one or two lab, which is like small clean room facility versus the big facility. Vacuum measurement techniques. What techniques are being covered in the device fabrication, that will cover under this section. And finally, challenges and innovations. Vacuum system technology. Basic definition of a vacuum is that vacuum is a condition where pressure is lower than atmospheric pressure, right? Meaning there are fewer gas molecules present in a given space. And based on the pressure, there are different type of vacuum. So low vacuum is from 133 to 1 130 133 1.33 and into 10 power minus 1, or in torr, mainly it's being considered in torr. 1 to 10 power minus 3, medium is from 10 power minus 3 to 10 power minus 5, high is from 10 power minus 5 to 10 power minus 8, and then ultra high 10 power minus 10 to 10 power minus 11, and when it goes further lower in 10 power minus 13, it's extreme ultra high vacuum. And after that, interstellar space, which is like in space, it's the vacuum is very high, or you can say pressure is very, very low. So that is 7.5 into 10 power minus 20. And in the industrial scale, the achievable limit up to 10 power minus 10 to 10 power minus 11. That's in the extreme cases. Now let's see why vacuum is so important in semiconductor processes. What's the unique property of a vacuum? So when we talk about the vacuum, we say it's a less pressure get reduced. So what's the advantage of it when pressure gets reduced? So it is being found that when pressure goes lower and the space is being created in a vacuum, the gas density also reduces of the molecules, and mean free path that increases, and time to reach by the particles to a specific distance that also increases. So these properties are very important, mainly mean free path. It's later we will see when we see the details of sputtering and thermal evaporation. Mean free path plays an important role. Gas density, it means like the contamination that reduces. So these are the unique properties of a vacuum that makes vacuum so important in semiconductor processes. In different semiconductor processes such as diffusion, ion implantation, those are very, very critical step, because in all all semiconductor devices, junctions are very, very important. That plays a major role. Let's take an example of BJT or MOSFET or simple diode. The junction takes all the control of the device, right? And when you perform those process, you do not want any contamination, any impurity in that process. And that is possible if you create a vacuum. Next, how vacuum is achieved. So vacuum is achieved by removing gas molecules from a sealed chamber using vacuum pumps. And here is a classification of different vacuum pumps. Now the industry has developed so far so different type of vacuums, and day by day their physics also improves, and in the market different type of pumps are being introduced, and the aim is to achieve vacuum level in very less time. So classification of vacuums, there are two type of pumps: gas transfer pump and entrapment pump. Gas transfer pump further differentiated into two parts: positive displacement, kinetic pump. And positive displacement is reciprocating and rotary pump. Kinetic pump, they are like drag pump, fluid entrainment pump. We not have to go in much detail into all these pumps. We mainly focus on what are being useful for our cases, especially in the semiconductor. We have like cryo pump, rotary pump, and oil pump, turbine pump. Those are some of the useful, but here is the complete list of different vacuum pumps exist in the market, and mainly two types: gas transfer and entrapment, and it's further being uh, classified into many different forms, such as like positive displacement has like reciprocating displacement pump, rotary pump, and then the gas transfer, the kinetic one, further has drag pump, fluid entrainment, ion transfer. uh, So this is a complete list, but we will focus on whatever pumps are useful for our cases, especially in the semiconductors. Here is the vacuum levels. So based on the different vacuum levels, their classes becomes differentiated. And in ultra high vacuum and high vacuum, it has the molecular flow. So that's why the process such as like ALD and uh, molecular beam epitaxy, these vacuum levels are being used. And whenever film thickness reduces, to grow that film, you have to use the high vacuums. Okay, because you are depositing in the atomic or in a molecular scale. uh, Other is medium and low vacuum, and it has just the viscous flow. Uh, from here, you cannot generalize that ultra high and high vacuum are always being preferred. So it depends on the application and what the film growth you need. Suppose you are growing a metal film or a semiconductor where your requirement is high orientation and the single crystalline epitaxy. You grow the ultra high and high, but whenever you are growing the insulator or dielectric, at that time you don't need those properties. So your work can be served from medium and low vacuum processes. So you cannot generalize that they can be underestimated. So all different vacuum levels are useful depending upon different applications. Next is the vacuum environment. So creation of different vacuum levels require different components such as pumping systems, piping. For measuring the vacuum levels accurately, it requires different techniques such as gauge types and physical processes. And mainly in the vacuum environment, you will see that there is a chamber, and in a chamber different piston screws are being connected. So the purpose is that in a chamber is a small room, and in a small room you do all the processing. So like miss, the way you cook and you use your stove, right? So this chamber is like your stove. So and then you are processing, you are making your recipes. And semiconductor is also like it's a process recipe, right? So but all the processes are being done in a vacuum. So we use a reaction chamber and we try to create vacuum in that chamber. So it's you can consider it's like it's a room, and I have to create a vacuum in that room. uh, how can we measure vacuum? So to ascertain the pressure level, gauges of different types are being used, such as direct gauges and indirect gauges. Direct gauges uses pressure from gas to deflect a needle or leave a column of mercury, and indirect uses heat transfer based on number of gas molecules present. Further, see the details of the direct type. Like mechanical gauges such as a diaphragm are used for rough vacuum. Pressure from the gas deflects the diaphragm. Indirect types has different thermocouples, filament heated by the constant current. heat transfer methods. So it uses a thermocouple that's used for rough to medium vacuum levels where direct pressure is too low to mechanically deflect a gauge. Uh, Another type of indirect is where the direct pressure is too low to mechanically deflect a gauge. So we use the ionization methods to measure the vacuum. And here is the typical ranges of different gauges. I'll not go much details into it, but just show that we have the solution at all different pressure level. And so far, we are capable to measure up to 10 power minus 10. In some advanced, it can measure up to like 10 power minus 11, 10 minus 12. Next one is the role of vacuum in semiconductor processes. So in device fabrication, we use lithography, PVD, CVD, plasma etching, ion implantation, and different type of coating techniques. And what techniques require vacuum, that will cover over here. So in lithography, vacuum is being used, especially in electron beam lithography. Next is physical vapor deposition. So that covers sputtering and evaporation, and both are dependent on vacuum. In CVD, there are different types: LPCVD, PECVD, UHV CVD. So LPCVD is low pressure CVD, PE is plasma enhanced chemical vapor deposition, UHV is ultra high vacuum chemical vapor deposition, then plasma etching, ion implantation. So in these semiconductor processes, we use vacuum quite a lot. So we see the details one by one, how vacuum is being used and what will happen if vacuum is not present or not being used, what harm it can do. In lithography first, objective of the process is to create temporary features on silicon wafer to guide etch and deposition processes. So in lithography process, we use different type of resist to make the patterns, and in device fabrication and the chips, there are multiple steps of lithography being used. So I have worked on the fabrication of solar cell, which is simply a PN junction device, but in the complete process, I use lithography up to 5 to 6 different steps. So first one was for the oxidation. The second one lithography was for the ion implantation, the third one for the back metal, and the fourth one was the front metal, and then fifth one was the final metal deposition. So that in one single PN junction diode device. So when you go for BJT, MOSFET, CMOS, there are multiple steps of lithography. In some cases, there are 14 to 16 different steps of lithography being used. And vacuum is so important in the lithography process. The role of vacuum in the process, there's one technique called E-beam lithography. So in E-beam lithography, it excludes atmospheric gases from lithography chamber to avoid particle collisions with beam and loss of energy. Vacuum eliminates secondary emission from particles that were inadvertently struck. And to perform all this process, extremely high vacuum levels are being required. Let's see some brief detail of electron beam lithography. So in an electron beam lithography, as you can see in this figure, there's an electron source, and that source release the electron beams of high energy that pass through a aperture, and then it flow through the signal flow through the condenser and deflector to focus, and then it goes through the mask, which is like a stencil over here, and then it directly go and react with the photoresist on the wafer. So it's scanning a focused beam of electrons to draw custom shapes on a surface covered with a resist. So electron beam changes the solubility of the resist, enabling selective removal of either the exposed or non-exposed region. So it's depend on what type of resist you use. In the case of positive photoresist, it selectively remove the exposed, and in the negative, it goes in the opposite direction. So it's a maskless lithography process. Here is a complete setup of electron beam lithography. So there is a computer control that goes through the high-speed data processing. It collects the data from beam blanking control and the beam deflection control. The signal which goes from electron gun to the final stage, it's being deflected from a mirror, and that's collected in a computer, and computer controls the beam blanking control, beam deflection, and the stage control. And AI plays an important role at this step whenever the signal is being processed in a high speed. So how vacuum plays role? In the absence of vacuum, there can be defects in e-beam lithography, and those defects are data-related defects and the physical defects. In the data-related, there are two types of defects: deflection error and the shaping error. And the physical defects, which is due to vacuum, that are outgassing, contamination, beam drift, and the back scattering. Vacuum levels, which are being used in EBL. EBL is a short form of electron beam lithography. One level of vacuum from 10 power minus 3 to 10 power minus 6 torr is being required in the load lock chamber. The load lock chamber is where the samples are being kept. It allows some sample exchange without exposing the main chamber to atmospheric pressure. Electron gun and the column. So over there, 10 power minus 7 to 10 power minus 9 torr. So it's a very, very high vacuum. This maintains a clean environment for stable electron emission. Sample stage chamber that maintains a 10 power minus 5 to 10 power minus 7 torr. This ensures minimal beam scattering and contamination during exposure. So here is a complete bench of the e-beam lithography and the electron beam stage that is further being shown in this extension picture. So vacuum generation and control, there are different type of pumps being used in EBL. So first one is the roughing. So it reduces pressure from atmospheric level to 10 power minus 3. And then the turbomolecular further decrease the pressure to 10 power minus 7 torr. And the cryo pumps or ion pump, this achieve ultra high vacuum 10 power minus 9 torr in the electron column. Role of vacuum in EBL process. So in the EBL, we need, first of all, very high vacuum, and the pattern sizes are very small. So that's the advantage of EBL over normal lithography technique. So role of vacuum in EBL, first one is the electron scattering prevention. High vacuum minimizes interaction between the electron beam and the gas molecules, preventing unwanted scattering that could blur the pattern. So when we have the electron gun over here, as shown in this picture, the electron beam goes through a focus in the earlier figure. Also, we have seen that it's here's the optical path of the electron gun. It passes through the aperture and the condenser and the deflector. So the beam should not deflect between electron source to deflector, and that is being maintained with the help of vacuum in the EBL process. So it's maintain the electron scattering prevention. Next is the contamination control. So the residual gases can cause contamination on the substrate, leading to defects in the resist layer. So the chamber where the samples are being kept, it should be free from the contamination, and that is maintained with the help of a vacuum. Next is stable beam operation. So this operation happens when the electron beam go and hit the substrate at the photoresist, and at that time consistency should be maintained. This happens with the help of the vacuum. So a consistent vacuum environment ensures stable electron trajectories and enhances resolution. Next is vacuum in deposition processes. Objective of the process is to add new layers or substances to a defined region of a silicon wafer. So we grow different type of films such as metal films, polymer, and the dielectric. The techniques we use in the deposition process, such as physical vapor deposition, this has two types, sputtering and evaporation. CVD has LPCVD and PECVD. First, let's see the detail of PVD and further look how vacuum plays an important role in PVD. Morphology of PVD, it's a high temperature is required to vaporize the material. Vacuum of different ranges is used, which depends on the mean free path required in the system. Remember this statement, the mean free path. Mean free path, when you have reduced vacuum, at that time, the mean free path of the molecules increases, and it gets sufficient distance and time to reach to the wafer. And vacuum plays an important role in increasing the mean free path. In the beginning of this presentation, I showed you the relation of the vacuum versus the mean free path. So as the vacuum increases, or like pressure reduces, the mean free path increases, right? So in PVD, we have the material in a solid form. So first we evaporate by different methods. It can convert into the gas phase, and then from the gas phase, it transport and deposit to the solid phase. So when it reach to the wafer, it becomes solidified over there. Thermal evaporation. First type of PVD is a thermal evaporation. In thermal evaporation, a resistive heating method is used. So in this process, the deposition is performed at high temperature and low vacuum. Vacuum decreases the content of contamination. Voltage and current are manually controlled. So in this process, as you can see in the figure, here's a substrate holder. We have the chamber, and in the chamber, the dots are being shown as the evaporated metal. And here are the coils. We place the metal wire, such as, aluminum in case of aluminum deposition, copper in case of copper deposition, or gold in the case of gold deposition. And due to the resistive heating, this material melts and solidify. So solid convert into the gas, and then it has the molecules has to reach to the substrate, and that to reach that substrate, it depends on the mean free path. So molecules travel a distance maximum up to mean free path, and in the vacuum, the mean free path increases so that particles get sufficient time and distance to reach to the substrate. Next is the sputtering. Sputtering is a plasma assisted technique that creates a vapor from the source through bombardment with the accelerated gaseous ions that is called plasma. The gas usually used in this process is argon, because it is non-reactive gas. So what happens in this case, we have the sputtering target, and the argon gas ions, they go and hit uh, with the target material and remove the material from the target. And that material, when it released because of the bombardment, it tried to reach to the substrate holder. And again, the vacuum and high mean free path helps those molecules to reach to the substrate holder. Plus, vacuum eliminates the contamination within the chamber. So sputtering work on the basis of momentum principle formed by collision of atoms and molecules. Plasma glow, ion accelerator or radioactive elements is used to evaporate material. Uh, Here are different modes of sputtering. Sputtering is being used in three different modes. First is the diode mode. So in that case, the target material. So target material is basically the material which you want to deposit on the substrate, right? So you make a target which is a pure form of that material. It's attached to the cathode, and the substrate upon which sputtered film is to be deposited is placed in an anode. So it's like a capacitor way. And when you apply the high voltage, it generates electric field between cathode and anode, and the molecules try to reach from the cathode to anode because of the influence of the electric field. And plus the argon gas also bombard and hit the target material and force them to release some atoms and molecules to reach to the substrate. Next is the triode mode. It adds a hot filament to the diode configuration, generate high density plasma independent of target excitation. And next one is the magnetron. So magnetron sputtering work on the principle of this. So that employs a magnetic field to increase the distance traveled by electrons, thus increasing the probability of their colliding with gas molecule to produce the ions needed for sputtering. So one extra feature added in the magnetron mode is you use this cathode and anode. Apart from it, you also use a magnetic field so that molecules get further more energy to reach to the substrate. PVD advantages. It's a high deposition rate technique. PVD gives high strength and durability. It has very good adhesion and hardness. Film is formed in PVD. There is less substrate surface damage from impinging atoms. Surface smoothness is very good. Because of high vacuum condition, PVD has excellent quality of the film. It has less tendency for unintentional heating of the substrate. So vacuum plays an important role in PVD. There are three different types of pumps being used to create the vacuum in PVD. First one is oil diffusion pump. Next is turbo pump. The third one is cryogenic pump. Oil diffusion pump, as the name suggests, oil. So we definitely use oil. So most common type of high vacuum is the oil diffusion. And in this case, oil is being heated and vaporized. Oil molecules collide with the gas molecules trapped inside the walls of the chamber, giving them a downward momentum, directing them out of the chamber. So what happens, we heat the oil, and oil molecules collide with the gas molecules. And so you can see like these are different arrows, and oil heat, it vaporize, and it collide with gas molecules, and they are trapped from these arrows. Okay, on the walls that give them the downward momentum and directing them out of the chamber. So that's how it creates the vacuum in the upper region of the chamber. Okay. Next is the turbo pump. Turbo pump is a mechanical pump. Turbine rotates fast enough to drive molecules. So as it's like a rotary pump which you use in a lab. So turbo pump is the extension of it. So it's a high vacuum pump which functions in a manner analogous to a diffusion pump. It has a backing pump to keep the fore pressure low to sustain molecular flow. And in this case, turbo molecules can cause momentum transfer impact with high speed. That turbine rotates from 2400 to 3600 RPM. And it's being helpful in the viscous flow of the material. Next is the cryogenic pump. It operates based on the cryopump. So it's like cryopump are also being used in cooling. In low temperature techniques, cryopumps are being used quite a lot. Operating parts of cryopumps are cooled metal surfaces installed inside the vacuum chamber. So pump operates at low pressure, where mean free path is on the order of the chamber dimensions, and cryopumps are free from oil, thus highly appealing for carbon-free film deposition. Next, see the vacuum levels used in the physical vapor deposition. First, let's see in the thermal evaporation. In thermal evaporation, there are two types of vacuums, base vacuum and deposition vacuum. In the base vacuum, it's from 10 power minus 6 to 10 power minus 8. And at the time of deposition, it reduces to 10 power minus 5 to 10 power minus 6. You can think that base vacuum is lower than the deposition one. At the time of deposition, vacuum further goes down because, okay, in a vacuum, don't confuse with the pressure. When I say high vacuum means low pressure. High vacuum means it's a space which has a higher vacuum than the other space. And when I say low vacuum means high pressure and vacuum is low over there. So at the time of deposition, I can say the pressure gets higher, right? But like vacuum is low. This happens because at the time of deposition, you are doing the resistive heating, and the resistive heating release the gas molecules of the target material. Because of that, and the vaporization of that is responsible for creating this vacuum to be higher in this case, especially at the time of deposition. But 10 to minus 5 to 10 minus 6 is still a very low number. So it eliminates the contamination even during the deposition. Vacuum levels in the sputtering. The base vacuum 10 power minus 6 to 10 power minus 8. But at the time of the deposition, it's 10 power minus 2 to 10 power minus 3. It optimizes ionization for efficient sputtering. It maintains good film properties. Role of vacuum in the sputtering. It prevents contamination. Because during the deposition, it reduces impurities such as oxygen, water vapor, and hydrocarbons that could degrade the deposited film. At the time of plasma creation, it maintains the right condition for ionizing the sputtering gas to create a stable plasma, because stable plasma is very required to achieve the stability of the final thin film growth. Vacuum, of course, it increases the mean free path. So this point you will see common in many techniques, the role of vacuum and its importance. In sputtering also enhances mean free path, affects the distance atoms travel before collision, influencing film uniformity and deposition rate. Next is the effect of vacuum on sputtering performance. When we grow the thin film, the film purity affects from the vacuum because lower base pressure reduce contamination, leading to high quality film. deposition rate, higher working pressure increases sputtering yield, but may reduce film uniformity. Film morphology, low pressure favor columnar growth, while higher pressure enhances scattering, leading to denser films. Plasma stability and optimized vacuum level ensure a stable and efficient plasma. And this picture shows the sputtering process trends for typical metals and the film. Uh, the step coverage for the metal and the film, it's different. And the deposition rate, uh, how it affect on the base pressure, sputtering pressure, and power, and the RF bias that's being presented over here in this table. And the step coverage is uh, is different in the sputtering than the CVD process. Uh, so overall, the vacuum plays an important role on the sputtering performance, because from the sputtering, we always require the high quality of the thin film, and vacuum help them to achieve those goals by providing the film purity, maintaining the deposition rate, maintain the film morphology and the plasma stability. Next, see the role of vacuum in evaporation. Earlier, we covered the sputtering. Now, come back to the evaporation. So, in the evaporation, again, it prevents contamination, because whenever you start the process, you always try to create the vacuum to eliminate oxygen, nitrogen, and other residual gases, which can degrade the film quality. So vacuum prevents the contamination. Vacuum enables controlled evaporation because it reduces unwanted interaction and ensures a uniform deposition rate. Enhances mean free path. So higher vacuum increases the mean free path, allowing them to travel to the substrate without scattering. Effect of vacuum on the evaporation performance. So as we have seen that in the evaporation, we have the resistive heating coil, and in some other evaporation process, we use a boat, and the boat is like a substrate, is a material holder, the material which we have to evaporate, melt and evaporate. So it's being presented from the green color, and these are like, the molecules of the vaporized material. And when it reaches to a substrate holder where substrate is being kept, it goes and deposit over there. So this all process happens in the vacuum. So the steps we earlier mentioned, like solid, gas, and solid. So to execute the complete process, high vacuum is always being maintained. High vacuum ensures minimal contamination, leading to high purity. It maintains the deposition rate. It maintains the uniformity, and it in the evaporation, there is the wide variety of materials, mainly the metals uh, and the organic based semiconductors. They need like high vapor pressure, which is possible under high vacuum to evaporate efficiently. Now let's see how different research groups uses the PVD and they report in the literature. I covered just one or two articles for each process. Because of the limited time, I cannot produce a complete review. But what different groups have found, I just provide a summary of it in one article of single source thermal evaporation growth and tuning surface passivation. So this group tried to create the perovskite film, which is the final combination of CS, PB, BR 0.5, CL 0.5 to the 3. And it started from the perovskite powder. and used in the perovskite solar cells. Here's a substrate holder on the top, and then the boat is being used. It contains the perovskite powder, and this goes through the high current source. When high current is being applied in the bottom portion, the boat is made up of tungsten, and the thin film growth on the substrate, which has a combination of CS, PB, BR 0.5, CL 0.5 to the 3. And in their study, they found that the theoretical data appeared inconsistency to experimental data. They achieved the uniform film growth. In the X-ray pattern, picture A shows the X-ray pattern, and so what it's trying to say that the experimental and theoretical, there's very good consistency, and that is possible uh, if the film growth is being processed in a very controlled way. So it's like, suppose you are cooking your food and you get the exact taste what you expected. So that happens when the theoretical data match with the experimental one. Uh, so this shows the capability of the process, how well you uh, perform the process. And PVD and mainly like sputtering, both sputtering and the thermal evaporation in the final film growth, uh, you can rely on it, and that is possible with the presence of the vacuum. Okay, now next one is the CVD process. This is another thin film growth process. It's the formation of a non-volatile solid film on a substrate by reaction of vapor phase chemicals that contain the required constituents. This process has several advantages, such as high purity deposit, a great variety of chemical compositions, fairly good film adherence, and good economy and process control. Uh, Deposition steps, the inert gases. What are the main deposition steps we use in the CVD process? So it's little different than the PVD. In PVD, the starting material is in the solid phase, right? And over here, it's in the gas phase. So it's a gaseous reaction in a reaction chamber, and they are driven to the surface of the substrate. The reactant gases are adsorbed on the substrate, and atoms form film by migration, and the byproducts, they are being removed from the reaction chamber. So in this process overall, we have a reaction chamber, one gas inlet, one gas outlet, and the substrate holder. So from the gas inlet, the gases are being introduced, they react and sit on the substrate. The byproduct is being removed from the reaction chamber. uh, so this table shows the comparison of three different CVD processes by their advantages, disadvantages, and their applications. So the vacuum is being used in low pressure and plasma enhanced chemical vapor deposition. And in the film growth, we will further move on to the LPCVD and PCVD and see how vacuum plays an important role in those processes. So here the reaction chamber is connected to a vacuum, as you can see in this picture. The pressure inside the chamber is pumped down to a required value. High vacuum cryopumps are being used in this case because they are oil free, and a temperature between 550 to 600 degrees centigrade was being maintained between the batch of the wafers. So in LPCVD, the advantage is it has a very high throughput, around like 100 to 200 wafers can be processed at a time. So there's a pressure gauge which measures the vacuum every time, and here's a vacuum brake valve. which maintains the vacuum inside the chamber during the gaseous reaction. Next is the plasma enhanced chemical vapor deposition. In this case, as the name suggests, plasma, so plasma is generated by application of a field, that's by creating free electrons within the discharge region. So plasma enhanced chemical vapor deposition. The advantage is it can operate at low temperature. So in this case, what happens that the difference between other CVD and PCVD is that you have the reaction chamber. The common thing is reaction chamber, gas inlet, and the gas outlet. Along with it, it also uses the plasma, so that when the gaseous reaction happen at that time, plasma assist uh, in the gaseous reaction and set the solid phase of the material onto the substrate. What are the different vacuum levels we use in different CVD processes? APCVD, we don't use vacuum. It's just at atmospheric pressure. So that's why there are disadvantages with the APCVD processes. So after that, there was a requirement to create the vacuum to reduce the contamination. So LPCVD and PCVD and UHCVD techniques were introduced. So LPCVD has 0.1 to 10 torr, so it's still higher vacuum. And PCVD it's further lower, 0.1 to 10 torr, and in ultra high vacuum CVD, 10-6 to 10⁻9 torr. In comparison to PVD, you can see that pressure levels are higher, but vacuum is still required in these cases because the vacuum cannot be maintained very high because it's a gaseous reaction, and introduction of that increases the vacuum, but it's still quite less than the atmospheric value. Atmospheric is like 760, and then LPCVD, PCVD are below 0.1. So that helps to eliminate the contamination quite a lot, and vacuum plays an important role in it. Ultra high vacuum CVD, this further improves the film quality and the growth. This maintains 10⁻6 to 10⁻9 torr. Now let's see the role of vacuum in CVD. Whenever I discuss the role of vacuum in different PVD, sputtering, thermal evaporation, CVD, many things you are seeing very, very common, such as like prevent contamination, enhances mean free path, plus some few points, but many points you will see common. And the common point like contamination enhances mean free path. So that's the overall aim of the vacuum. Okay, so it affects in CVD as well. So it reduces the contaminants such as oxygen, moisture, and hydrocarbons that could degrade the film quality. So that's being prevented with the help of vacuum. It controls the gas flow and pressure. It maintains a stable and uniform precursors gas distribution. It enhances the mean free path. It regulates reaction kinetics, which adjusts vacuum levels, influences surface reaction and growth rate. So depending upon the reaction and the input conditions, vacuum is supportive in all those conditions. Effect of vacuum on CVD performance. So it helps in achieving high film uniformity. Growth rate being controlled with the help of vacuum in CVD. It results in material purity. It reduces unintentional doping and contamination, so which maintains the material purity in CVD. Adhesion and density, optimize pressure conditions, improve film adhesion and the density on CVD. Now let's see what's the different research group says. And again, like I'm just providing the example, one or two example of each technique. So in this article, this was published in Nature Communications. Uh, it's a giant enhancement in vertical conductivity of stacked CVD graphene sheets by self-assembled molecular layers. So they grow the CVD, graphene stack from CVD technique. The advantage of graphene is the high conductivity. So they compare two cases, one the graphene to graphene stack layer, another graphene and self-assembled monolayer and graphene. And they found that with the deposition of the P base, the conductivity further improves. And both processes were done from the CVD. And most of the graphene-based FET, they rely on CVD, CVD-grown graphene, which is the deposition of the stack layer in layer by layer manner. Overall conductivity improves with the layer thickness uh, because there is like weak electronic coupling between the layers. In CVD, there's a weak electronic coupling that improves with the deposition of P base. So they compare uh, deposition of like P base along with the graphene. So in the figure, you see like G versus G, and here in the figure B, it's G versus P base versus G. So P base is a self-assembled mono layer, but overall growth they are doing from the CVD, and they found the high film quality. In this figure, they measured the tunneling current density and SM growth time. The log average current density increases sharply to 10 power 3 and saturates after 24 hours of SAM growth. So the self-assembled monolayer that's been grown at different times in the processing. So different saturations. So self-assembled monolayer in the green curve saturated start from the like 0 hour and then 4 hour maximum up to like 36 hour. And each has its advantages. So film which grown for higher time that showed the lower tunneling current density. In another research article, Enhanced Light Trapping in Thin Film Solar Cells, uh, we published this article in 2015, and we used the plasmonic fishnet structure in the film growth of amorphous silicon. So this is a stack of ASIO versus ASIO. That is the aluminum dope zinc oxide, and this is a transparent film. So the application is in the thin film silicon solar cells. On the back spacer, if we use this fishnet structure, this was grown from electron beam lithography technique. So what we did, we performed the deposition of the silver, and then on top of it, we use the positive photoresist and develop it after the e-beam lithography exposure. So we use e-beam lithography technique, and that e-beam lithography expose the portions because we use a positive photoresist. After that, we did the developing, and that make the final silver patterns which look like a fishnet structure. That's why we give the name the fishnet AG, and the width of those lines are up to 100 nanometer, and the center to center spacing is 600 nanometer. In this case, the amorphous silicon that was done using plasma enhanced chemical vapor deposition under 900 millitorr at 50 watt power for 17 minutes, and we grow around 500 nanometer thick layer. And overall, the advantage of using the fishnet was clearly observed in the absorption measurement. This was done from ellipsometer, and this graph shows the effect of individual layers and amorphous silicon that is responsible for around 82% of the total absorption within it's within the amorphous silicon layer. And here is the SEM image of the fishnet structure. Earlier in the figure, I showed that it's a 600 nanometer and the 100 nanometer. So that's the same feature we got from the SEM. So these are the SEM images. Total absorption of the comparison with and without fishnet structure. So with fishnet, it's clearly visible in the absorption measurement. With fishnet, the absorption increases, especially at around 700 nanometer. And in solar cell, this means a lot. Because in solar cells, it's being deal in the visible range from 400 nanometer to 700 nanometer, and the quantum efficiency is the integration under this curve. And absorption increase at 700 nanometer reflects in the quantum efficiency of the solar cells, and thus it plays an important role in the light enhancement of the thin film solar cells, mainly the absorption parameter of it. The second figure shows the repeatability of the absorption measurement from four different type of fishnet structures in four different samples, and it maintained the continuity. So overall, CVD is also results in high quality of film growth, and that happens due to the presence of vacuum. Now let's see the vacuum in ion implantation, how it works in ion implantation. Ion implantation is a low temperature process by which ions of one element are accelerated into the solid target. So here you are seeing that ions, they are being released. They travel through a different step, and each step is responsible for the signal enhancement and the beam enhancement, and reach to the sample stage, which is shown from the blue color over here. So it's a low temperature process, and ions has to travel from source to the sample stage. Ions can alter the element's composition of the target. The ions, and these ions are statically accelerated to high energy using a radio frequency in the target chamber where ions impinge on a target. Here, in this case, the ion beam synthesis happens in the ion implantation. The difference between the ion implantation and the diffusion is the growth of the substance. So in ion implantation, it grows more uniformly than in the diffusion, and it has typical ion energies are in the range of 10 to 500 kilo electron volt. It has one disadvantage of creating the damage in the surface material, and that can be controlled by controlling the energy input. Overall, it available from 10 to 500 kilo electron volts. In the processing range, mainly 1 to 10 kilo electron volt is being used. I have used ion implantation in one of my process when I was doing the fabrication of solar cells, and we use around like 5 kilo electron volt to create the dose for the p-type silicon wafer. In this case, it is showing 10 nanometer thick SiO2 layer implanted with 1 kilo electron volt silicon plus ions, and the XTEM images shows at two different type of doses, and one is for like 1 into 10 power 16, and another is 2 into 10 power 16. And the film growth was pretty uniform from the ion implantation. Uh, the vacuum levels which are being used in ion implantation are 10 power minus 6 to 10 minus 8 torr for the base vacuum, and for the operational vacuum, it's 10 power minus 5 to 10 power minus 7 torr. So to create the base vacuum, it remove the residual gases first from the chamber, and at the time of operational vacuum, it maintained during implantation to ensure ion transport without scattering. So ions has to transport from the hollow cathode hot filament source to the load locked chamber. How vacuum plays an important role in ion implantation? It prevents contamination. Again, you see, like it's very much common. It ensure accurate ion beam control. A vacuum environment allows ion to travel without scattering or colliding with the gas molecules, ensuring precise doping concentration. It reduces scattering and beam loss. Low pressure increases the mean free path, preventing undesirable deflection through alter implantation profiles. It maintains stable plasma generation. So ion source in the implanter operates efficiently under vacuum, ensuring a stable and consistent ion beam. And you can see in this picture, we have the electrical system and the vacuum is connected over here when the ion is started from the ion source and throughout the beam line until it reaches to the electrical system, and its whole chamber is being managed under the vacuum, and vacuum is being controlled in different section in a different way. Effect of vacuum on the implantation quality. So it maintains the precision and the uniformity of the thin films, which ensures accurate ion dose and the depth control. Here, the ions are being implanted, so the purity of that material is very important. So that plays an important role. Doping efficiency reduces unwanted ion collision, leading to a well-defined doping profile. This happens with the help of vacuum. Film integrity prevents oxidation and contamination, ensuring high purity semiconductor materials. And this also achieved with the help of vacuum. So the depth profile in ion implantation and in the diffusion is very much different. So this is the typical concentration with respect to the depth in ion implantation. So we see the mainly the good Gaussian. So we need the good peak intensity, and that maintain with the help of the vacuum. Otherwise, there will be the presence of other gases and the material which can affect the film quality, and it results in a poor junction of the semiconductor devices. In semiconductor devices, ion implantation and diffusion, these two are very important steps, because in semiconductor devices, junction is almost everything. And if you compare different processes, such as CVD, PVD, and the diffusion, ion implantation, and many other like lithography techniques, out of all those techniques, diffusion and ion implantation is something which need to be taken care of very seriously, because there are some mistakes which you can eliminate, and there are some mistakes you cannot have second chance. right? So diffusion and ion implantation are one of those. And at that time, vacuum is being used, and it plays a very, very critical role in the quality of the final semiconductor device. Now let's see the importance of vacuum in semiconductor manufacturing. Earlier, we saw how vacuum is being used in different semiconductor processes. Now let's see its importance in different ways. So reason for maintaining a vacuum is very important. There are three main reasons. First is controlling contamination. Second is enhancing process control and yield improvement and the cost reduction. Controlling contamination. Why it is so important in controlling the contamination? So far we have seen different semiconductor processes, and each step, whenever I say role of vacuum, my first point was always controlling contamination, right? Why it is so important? It prevents defects in microchips. It eliminates unwanted particles, moisture, and organic contaminants to prevent oxidation by removing atmospheric gases like O2 and N2. And miss overall clean room. We earlier we saw like class 100, class 1000, class 10,000, and it eliminate uh, the dust count. So over there also, like you cannot say that clean room is a vacuum. No, it's not true. But overall, there's a flow of the gases and flow of the air. That air blows in and air blows out. So in the clean room, what happens that from the top portion you have the air that apply forces on the dust particle, and those dust particle from the gravity goes down and then collected from the floor. It reduces the pressure than the atmospheric, but not in very, because it's not eliminating the gas particles. Uh, but overall aim is that somehow to control the contamination, to reduce the dust particle, or to reduce the unwanted material, not to not to interfere when I'm doing one of my process, right? So it's simply like, I always try to compare the semiconductor processing as like, the way you cook your food. So if you are like, cooking your food, instead of salt, if you add sugar into it, or some content of sugar into it, it's like make the food bad, right? So the same thing happen. You are doing the semiconductor processing, and at that time some more like those unwanted spices come into your picture, right? In your food. So those unwanted materials come during your semiconductor process, so that affect the film quality. So controlling contamination is that much important. So it prevent defects in microchips, it eliminate unwanted particles, moisture, and organic contaminants. It prevent oxidation by removing atmospheric gases like O2 and N2. Uh, Now let's see what type of contaminations exist. So what are the main contaminants? So first one is the particulate contaminants. So it cover the dust and airborne particles such as fibers, skin flakes, and clothing lint. Metallic particles such as aluminum, copper, iron from equipment wear. So, okay, first one, dust and airborne particles, fibers. So you have seen that in a clean room, whenever we go, we just wear the astronaut suit, right? So that gown is being designed in a way that it release very less flake and the clothing lint. Overall aim is to remove the dust. Second is the metallic particles. In the lab environment, whenever we deal with different materials, they are also being introduced in the environment, and that act as a particulate content. from bare eyes, it is difficult to see those because they are in a very small concentration and we cannot see from our eyes, but they exist in the environment overall. So these contaminants are like aluminum, copper, iron from equipment where there are silicon particles because most of the time we deal with a silicon wafer and it releases from the wafer dicing, etching, and the grinding processes. There are chemical residues such as dry droplets from chemical processes. Second type of contaminants are chemical contaminants. So those are organic, such as photoresist, hydrocarbon wafers, inorganic contaminants such as sodium, potassium, chlorine. Uh, the third one is the airborne molecular type of contaminants. So the picture on the right side shows the as the semiconductor process get advanced from 1990 to 2025, the overall aim and with the development, we have come up with the solution where the contamination concentration it's being reduced, but now the demand is also high. So the demand says that it should be like parts per trillion. Okay, and number of possible contaminants as the bad news we can say is also like because of the high demand, contaminants also being increased because as you grow smaller in size or miniaturization or you can say AI, uh, it's overall mm, like the Moore's law covers like billions of transistor, so it goes through multiple steps, like the number of processing steps also increase. You can say yes, film quality improves, yes, we agree, but at the same time the number of process steps also being increased to make the film quality better. So again, like you can compare that if you want to make good dish, you add like more ingredients into it. So that's happen over here. So you have like precise control. So the main drawback of that is that number of possible contaminants, as you can see in this picture, that's also increases, and that's why the demand is to control up to parts per trillion. So it's a very nice picture uh, of like the AMC control and the number of possible contaminants the with respect to the time, and it's a very advanced like very recent and covers up to like 2025. uh, okay, so here this figure shows the comparison of technologies above and below 5 nanometer. So up to 5 nanometer, if I make a boundary over here, so this ends up to like 100 parts per trillion to 10 parts per trillion, and that as the advancement goes and then the feature sizes go below 5 nanometer node, then the demand is to control the contamination up to parts per trillion. Uh, so first, these two like or chemical and particulate contaminants, these two are like two very important. That's why like they are placed first. Other one are like the metallic contaminants, which covers the transition metal. This was also covered in first point, but in the first one we just say like aluminum, copper, which are mainly from the processes, but there could be more in that list, such as transition metals. And the heavy metals such as PB, lead, cadmium, which can cause defects in semiconductor devices. The next one is the gaseous contaminants, that covers the process gas impurities such as moisture, oxygen, hydrocarbons, and the corrosive gases. Because in the CVD and in the etching process, we deal with many gases such as HF, HCl, NO2, and some more. So that also creates the gaseous contaminants, and the gaseous species can also react and convert into a solid phase, so that can also create a contaminant. Uh, there are other in the biomedical field because the uh, lab on a chip and organ on a chip is the next advancement. So on those applications, biological contaminants is also a challenge. So such as like bacteria, fungi, mold, spores can interfere with photolithography and the wet processing that results in a contaminant and affect the film quality. There are other such as human contaminants such as sweat, hair, skin flakes, saliva that also come into the category of biological contaminants. Uh, the next category is the electrical contaminants that cover the electrostatic discharge caused by charged surfaces, personal or the tools. There are mobile ions such as sodium, potassium, which can migrate in the semiconductor layers and degrade device performance. Plus, there are some cross contamination from equipment and material that covers the process chamber residues, such as deposition film, polymer buildup in the etchers, substrate cross section, substrate cross contaminations, such as wafer carrier particles, mass contamination, tool bag contamination. Covers the contamination from previous wafers processed in the shared tool. In the uh, the processing uh, of there are some YouTube videos available of the Intel and the TSMC. So they show very nice process with the robot. That robot is like a box, okay, with a and that maintain a vacuum. And what it does, it transfer the wafer from one process to another process, and in a line they go all in a line, and very nice animation and video was being shared by TSMC, and that is the best example of the cross contamination. So when the wafers are being transferred from one process to another process, cross contamination is also challenging, especially below 5 nanometer technology. Next, in the importance of vacuum is the enhancing process control. Uh, in different process, earlier we saw uh, how vacuum is being used, and now let's see in brief how vacuum plays an important role in enhancing process control. So in PVD, CVD required control vacuums to achieve uniform and defect-free within thin films. Uh, Sputtering and evaporation techniques depend on the vacuum to prevent impurities and ensure precise layer thickness. Uh, Another CVD technique such as ALD, the ALD uses vacuum to control chemical reactions for atomic level film growth. So here are three pictures which shows the importance of vacuum. So you can see in the PVD process, we have the coating material. This is the represent from the red color. So this has to be coated onto the surface. Okay, so and this has to reach a path from here, from coating material to the surface to be coated. In atmospheric pressure, you see a lot of particles such as vapor, oxygen, nitrogen, and many other molecules in the air. And it is not possible in the first figure, right? And when you create the vacuum, and it's a low vacuum, these blue particles, they will scatter with it. So it's again affect the film quality. And the high vacuum, they are further being eliminated, and they can easily deposit. Next is the plasma based etching and cleaning. High level of precision in material removal is possible with the help of vacuum. Uh, it affects the surface modification because plasma composition, energy, and exposure time can be maintained stable. With the help of vacuum, it minimizes damage to underlying material. Plasma-based etching is a dry etching technique, and in this technique, the plasma is being maintained, and it goes and hit the material, collide with the material, remove the material, and as photoresist portions are uh, being remain safe, uh, and the vacuum is being required to maintain during the process to achieve the high level of precision. Next is the ion implantation and doping. So earlier we saw how the vacuum is being used. Now see the importance of vacuum in the ion implantation. Ion beams has to travel a path from ion source to the base material. And in this travel of the beam from source to this, source to the sample base material, the vacuum has to be maintained at each different step. So it first goes through the extraction voltage, which is passing through the ion electrode. Next chamber is the analyzing magnet to maintain the path, and the magnet uh, helps to deflect the beam, which is passed through the mass separation slit, and then it travels through the ion acceleration column, where it's being uh, further experience the deflector to maintain the focus of the beam. Magnet maintains the stability of the beam to further travel to the electronic scanning, and then it goes to the sample. So at each different step, vacuum maintain the energy of the beam and the direction without scattering. At any step, if there is some scattering, then the ion energy will be lot different what it released from the ion source, and it reaches to the sample. Uh, Vacuum maintains accurate implantation depth. This is possible with the help of maintaining control energy and the dose. And the dopant uniformity for semiconductor devices can be maintained with the help of vacuum in the ion implantation process. Now let's see the importance of vacuum in the lithography process stability. It prevents the contamination. It provides consistent exposure conditions. It maintains uniform resist coating, enhance etching and developing process critical for EUV lithography, and improve adhesion and pattern transfer. So now let's see one by one the detail of all these processes. First is the prevention of the contamination. In lithography process, even minuscule contaminants can cause defects. Suppose you are doing the photoresist spin coating, and at that time the vacuum is not maintained properly. It introduces some airborne particles, moisture, and organic contaminants that can be minimized with the use of vacuum. Next is vacuum maintain the consistent exposure condition. In DUV and EUV processes, it requires highly controlled exposure conditions, and vacuum ensures consistent light propagation and precise pattern transfer. Vacuum maintain uniform resist coating by removing the air bubbles in the photoresist. It also prevent defects during soft and post-exposure bake in the lithography process. Vacuum enhance etching and developing processes by ensuring uniform chemical distribution during dry etching and resist development. Vacuum reduces variation in feature profiles and critical dimensions. is critical for EUV lithography. This is extreme ultraviolet lithography. This operates at 35 nanometer feature sizes, which is highly absorbed by air, and vacuum is required to prevent EUV absorption and maintain stable patterning. It improves adhesion in pattern transfer by providing the surface cleaning before resist coating. Vacuum ensures precise wafer alignment, prevent slippage in stepper and scanner systems. Next one is reduce outgassing and defects. So vacuum baking before exposure removes trapped gases and volatile residues, which prevents the outgassing, and that further prevents contamination of the reflective optics. So overall conclusion is that maintaining a high vacuum is essential for minimizing defects, ensuring uniform resist application, improving pattern fidelity, and enhancing throughput in the lithography process. Next is the yield improvement and the cost reduction. Wafer yield management in semiconductor manufacturing depends on the ramping, tracking, automated tracking, and the real-time detection. And vacuum plays an important role by enhancing process consistency, minimize variability, improve plasma stability, and reduce downtime. So this overall affect the yield and the cost reduction of the final semiconductor devices. Now let's see the control of vacuum lines in semiconductor manufacturing. The way we control the vacuum in different chambers and when it goes into the processing line, it's a lot different. The key components of vacuum lines are the vacuum pumps, valve for flow control, pressure sensors and controllers, load locks and interlocks, automated vacuum control systems, and common control strategies. So this picture shows that different process gases, they are being means like instead in a what the setup we see in the lab scale is a lot different than in the manufacturing floor, right? So if you see in the clean room, we use some glimpse of small manufacturing, but overall in the manufacturing, it further uses different type of lines. The gas lines are different and the vacuum lines are different. Apart from it, for the extreme ultra high vacuum and ultra high vacuum technologies, some more turbo pumps are being connected to provide the high vacuum on those processes. So overall, this is the chart of the different lines, goes through different steps. And let's see the details of one by one where vacuum are being used in those lines. So there are like a roughing pump line that's used for initial evacuation, and the high vacuum lines such as turbomolecular, cryogenic, and ion that maintain stable process vacuum. The valves for flow control, they are also dependent on the vacuum. So they gate valves, butterfly valves, pendulum valves, they are also being used in the vacuum line. It's a control isolation between chambers, and it adjusts flow rates for precise vacuum regulation. The third one, pendulum, that used in process require fine control over gas flow. In the semiconductor processing, we use different type of pressure sensors and controllers. Those are of different types, such as capacitive manometers, Pirani ion gauge, mass flow controllers. So they measure the pressure for real time in different vacuum ranges and regulate gas introduction into the chamber. So vacuum plays again important role in that. Load locks and the interlock. So we use different type of load lock chambers and safety interlocks, and they use the vacuum In load lock chambers, it maintains vacuum when transferring wafers to prevent exposure to air. Uh, and Safety interlock prevent accidental chamber venting and protect sensitive wafers. Next is the automated vacuum control systems. So we use different PLCs, SCADA, and feedback loops. So first is PLC. In PLC, it uses vacuum to manage pump sequencing and the valve operation. SCADA is supervisory control and data acquisition. This is used to monitor and adjust vacuum parameters remotely. Feedback loops. In this feedback loop, different type of sensors are being used which provide real-time pressure data to adjust pumps and valves dynamically. Next is the common control strategies. So these are like pump down sequence optimization, process stabilization algorithms, leak deflection alarms. This ensures efficient evacuation without damaging wafers, maintain a constant vacuum during deposition, identify and respond to system leaks to avoid process failures. So overall benefits of effective vacuum line control is that it improves process stability, reduce contamination, enhance yield and throughput, low downtime, and the maintenance cost. Uh, Next is the vacuum measurement technique in semiconductor manufacturing. This table shows different pressure ranges require specific vacuum gauges. We have three different type of vacuum: low to medium, high, and ultra high. And based on different vacuum level, different gauges are being used. So for low to medium, we use Pirani and thermocouple. For high vacuum, we use capacitance, cold cathode ionization, hot cathode ionization. And for ultra high, we use Baird and spinning rotor. Uh, let's see a very brief detail about the different gauges which are being used at different vacuum level. For low to medium, we use Pirani gauge. It operates on the principle of thermal conductivity changes due to gas pressure variation. Uh, each process has its advantage and limitation, right? And thermocouple, it's used similar to Pirani gauge, but uses thermocouple sensor for more stable reading. High vacuum, it uses capacitance manometer, cold cathode ionization gauge, and hot cathode ionization gauge. Uh, Each process has its own uh, uh, operating principle. So capacitance manometer measure pressure by detecting diaphragm deflection. Cold cathode uses high voltage discharge to ionize gas molecule, measure ion current. Next is the hot cathode. So it's work on the principle of electron impact ionization of gas molecules that produces an ion current. Uh, Third category is the ultra high vacuum. This is measured using Baird Alpert gauge. It uses a fine wire to reduce electron interaction with the sensor, improving the sensitivity. Uh, Next is the spinning rotor gauge. It measures the gas viscosity uh, effect on the rotating ball. With respect to different vacuum, different gauges are being used. And let me just finalize the talk with the future challenges and the innovations. So there are challenges in vacuum technology which is required to be solved. Uh, there are molecular contamination, process control, stability, energy consumption, and sustainability. And future innovations in vacuum technology are required in advancement of pumping technology, smart vacuum monitoring and automation, sustainable and eco-friendly vacuum solutions. First, let's see the challenges. The first one is achieving and maintaining ultra high vacuum, because with the advancement, vacuum requirement will be that every process will ask, I need high vacuum, right? And maintaining high vacuum is not easy task, and it needs lot of arrangement, and such as the molecular contamination, outgassing from chamber walls, seals, and materials introduce residual gases that require extensive breakout procedures. So that come under the category of molecular contamination. Leak detection and sealing issues is another challenge. There's a micro leak in large vacuum chambers or high temperature environment reduce vacuum efficiency. Third one is the pump efficiency and the lifetime. As pump goes old, its efficiency reduces, like same as the battery and many other electronic devices. So it happens to the pumps as well. So turbomolecular pumps and cryo pumps require constant maintenance due to mechanical wear and particle contamination. Uh, so these are challenges for achieving and maintaining ultra high vacuum. Another challenge is to maintain the process stability, process control and stability. Uh, it covers pressure fluctuations. So pressure fluctuation is another challenge because uh, maintaining a precise vacuum level is crucial for semiconductor fabrication and the thin film deposition. And pressure fluctuation affect the film growth. Plasma instability in ionized gas environment is another challenge, and that affect the semiconductor process stability. So plasma etching, sputtering, vacuum fluctuations that lead to unstable plasma formation, affecting film quality. The third challenge is the energy consumption and the sustainability. Vacuum process require high power because they operate at high voltage, especially the cryogenic and diffusion pump consume significantly high energy. Environmental concerns also involved with the vacuum process. So vacuum pumps release oil, vapor, and greenhouse gases, which are harmful for the environment. Material and the waste management, disposal of spent absorbents in cryopumps and oil contamination in rotary pumps creates sustainability issues. Future innovations in vacuum technology. We need advanced pumping technologies, dry vacuum process, because we already saw that oil waste goes into the environment that is not environment friendly. So we need dry vacuum pumps, oil-free, high-efficiency alternatives that reduce contamination and maintain cost. Turbomolecular pumps with magnetic bearing, it eliminates friction, extending pump life. Cryogenic vacuum pumps with regenerative cooling, uh, because it uses the closed cycle refrigeration to enhance efficiency and reduce helium consumption. Uh, so that further needs to be advanced to overcome this challenge. Smart vacuum monitoring and automation is being required in vacuum technology. So we need AI-driven pressure control systems, so adaptive algorithms optimize vacuum stability in real time. IoT-enabled vacuum sensors, because many times we need the smart process execution, and that is possible with the IoT, and that is the future innovation in vacuum technology. Smart diagnostic predict failures and optimize maintenance schedules. Real-time leak detection with mass spectrometry. Leak detection is one challenge in vacuum technology, and with the innovation of mass spectrometry, we can overcome this challenge. So advances in residual gas analyzers help identify, eliminate leak faster, and that further need to be advanced, and that is possible with mass spectrometry. Sustainable and eco-friendly vacuum solutions are being required. Uh, so green vacuum technologies are being required, which is possible with the development of low pressure, oil-free and water-free vacuum systems that will minimize environmental impact. Recycling and regeneration of cryogenic coolants are being required, so they need to be advanced so that they can reduce helium consumption through closed loop recovery system. High vacuum systems are being required and should be innovated to integrate physical and chemical techniques, physical and chemical vacuum techniques that can optimize energy usage. So I just give break to myself, and that's the overall of my presentation. I would like to thanks again to the organizing committee. I hope that I finish on time, and now I'm ready for the questions. Hello.
Yeah, I am here. So yes, the questions are here. It was a wonderful presentation. Yeah, Bhavnari, you can please ask your question.
Thank you, ma'am. Thanks for the detailed presentation, sir. Sir, I would like to know, I have two questions. One is like when you showed the silicon wafer in one of the slides, a bigger one, it looks like the edges of the silicon wafer are not used. Even some of the companies right now, they are trying to work on utilizing the edges, like 20 to 30% of the silicon wafer at the circumference. It is not utilized for silicon fabrication. So they're trying to utilize. What could be the factors that that area of the silicon which is going as a waste can be utilized? Because silicon processing itself is a high pure and high temperature.
Yeah, no, that's a very good question. So most of the time it happens that the Czochralski process uh, produces the circular size of the wafers, right? And over there, when you make a chip, those chips, they are either rectangular size or the uh, square shape, right? Mostly rectangle. And from suppose you draw a circle and you take out different rectangles out of it. So at the circumference, you will always have some waste. So they try to minimize that, but one has to go with it because you are cutting rectangles out of a circular shape. So at the circumference, there is always the material waste. And that can be minimized. Minimize is not really possible, but what companies they are doing, they are producing, especially the Intel, IBM, and other big manufacturers, they are trying to use like big size of the wafer so that like many chips can be cut at a time and processed at a time. Uh, so hope this will answer your question.
Thank you, sir. Yes, one more. I have one more question, sir. Like in the vacuum systems, we use water circulation to maintain the temperature. So, and also at a high vacuum, mean free path for the molecules are very high, and they are aligned towards the edges of the walls of the container or the chamber. So, in this case, when we do the water circulation, how it is going to affect the vacuum that is being produced?
Yeah. So yeah, so where it goes to the wall of that chamber. So what people do to minimize the contamination on the wafer quality or on the final semiconductor device, they dedicate one equipment for one material. So let's say in one chamber you are using copper deposition, then you avoid to do the gold deposition on the same chamber. Because in that chamber, when you do the thermal evaporation or the PVD, you will have the copper residues because copper will deposit everywhere on the wall, and and next time if you do the gold deposition on the same chamber, then the copper residues may affect the film quality. But if it's already being copper and then you are going to deposit copper, that can eliminate this effect. And there are other techniques. People, what they do, they do the cleaning, because we have to accept the reality that PVD processes, many times the chamber that gets affected. In small scale, people clean it regularly, or in a high manufacturing, if it is not possible, people do it on a monthly basis. But overall, they what the best practice they do, they dedicate one material for one process. Suppose you are doing PVD of copper and nickel and gold, then you use three different chambers instead of. I know, like, no, you can question that it will further increase the cost, but in a high manufacturing, uh, they are more concerned about the contamination rather than the cost of that, because they are making in millions, millions or billions of chip. So contamination is more serious concern for them.
Thank you, sir. One last question, sir. Like, also, when you use the diffusion pump, oil is going into the chamber and uh, promoting in the vacuum formation to higher torque, in the sense like 10 power minus 3 to 10 power minus 6 or 10 power minus 7 in the initial slides which you have showed. So how that when the oil enters the chamber, oil vapor of the oil or something, how it is going to function,
Yeah, no,
because
actually,
the quality of the
yeah.
film.
Yeah. No, actually, again, it's a good question. So what happens that when actually they are being designed in a way that uh, from the figure it looks that oil uh, goes into the chamber, but it's being eliminated quite a lot. Because overall the oil quality that sorry uh, the quality of the final film that may affect, but it's being designed in a way that the vapors of the oil that goes and then they deflect from their path. So overall, the in the designing of the process, it's being considered that uh, the whole environment is totally free of the oil. And at the time of the deposition, only that time the wafers are being exposed to the chamber. Rest other time, it's like, whenever you go in an event, first they do the preparation, right? So the oil pump, the purpose is uh, like, do the preparation for the process. So the preparation means maintaining the vacuum. So maintaining the vacuum and eliminate all the gas molecules from the chamber. And the designing of this process is being done in such a way that only at the time of processing the samples are being exposed, and rest of the time it's maintain the vacuum. And when the samples are being targeted to hit with the plasma, at that time the samples are being exposed. Uh, uh, from a theoretical point of view and reality, you can say that, like, nothing is perfect, nothing is 100% in physics, but that percentage is very, very less. If you count overall, it is less than 0.15%. I don't know the exact number, but I would say it can be like 0.001, 0.002, but it's very, very less.
Thank you, sir. Thank you very much.
Yeah, welcome.
There is one more question in the chat box. What is the difference between working pressure and deposition pressure during PVD?
Yeah, working pressure, deposition pressure. Working pressure is when the pressure is being maintained in the chamber using the roughing valve and the backing valve. So these two are the pumps. And deposition, when you deposit the material, such as in PVD, you heat the material and then let me just. Okay, so deposition, the pressure chamber is like you are maintaining the vacuum and then create the vacuum in the chamber. And the deposition means when you heat the material, at that time the material comes into the gas phase, and that also affect the pressure. So it increases the pressure. So that is a deposition pressure. And in one table, I remember I showed yeah, see here, the base vacuum and the deposition vacuum. So during the evaporation, because now the metal particles are in the chamber, and that affect the base pressure. So it increases the pressure in the chamber. That's why these are like two different pressure values. Yeah.
I hope, Jyoti, your query is resolved. Another question is how you clean oil spill up in chamber diffusion pump malfunction? What is the best ways?
Yeah, yeah. Actually, with the innovation, this will again possible. But I know, like it says the oil diffusion pump. Uh, the design of this is being done in a way that it doesn't introduce any oil particle or any oil dust in to the chamber. That value is very less. And further in the design, the innovations are being done. It's a point of the future innovation, but overall this concern is very less, because this technology is being in the business for the last 50 years. And the oil effect in the final material quality, that possibility is very less, because in the PVD and PCVD, mainly PVD I would count, where in the high vacuum the oil diffusion pump is being used. In the final film material, the oil content from the XRD was I have never seen where it was being noticed in the XRD techniques or any SEM technique.
Right. So there is one more question. What could be the reason due to which a turbomolecular pump stops working during the deposition process?
Yeah, actually in PVD it goes in steps. The first step is the backing valve. So and then it goes to the roughing, and then it goes to the oil one. So it goes in step. So whenever you want to achieve the high vacuum, this is not possible at one step. This goes in different steps. So it's like you can relate that. Suppose you want to do a task and you use skill of three people. Okay, so first level of people is like who maintain small vacuums, medium level who maintain like higher, and the third level is further higher. So that's happened in the vacuum deposition processes whenever high vacuum is being required. So the first level of pump maintain up to like 0.1 to 10 power minus 3, and then the medium one that goes up to like 10 power minus 4, and then the higher one -5 to -7. So it goes in three different steps. Then one can achieve the high vacuum. And this is common in many different process, whether it is like electron beam lithography or PVD. In PVD process, most of the time you will see that these are the steps. Whenever somebody work on those tools, they go and turn on the backing valve. And when the backing valve achieve the pressure up to 10 power minus 1, they turn off and then do the roughing valve. Okay, and when the roughing maintain up to like 10 power minus 3, achieve up to 10 power minus 3, 10 minus 4, then they do the they shift to the another one. So it goes in those 3 steps. So you can compare, like, suppose like, I have to do a work and then 3 people are being required, right? So the first level of person, he do his job, second level of person, he do his job, and then third level of person, he do his further job. And you can compare the first level person has limited skill, medium skill, and high skill. So that happen in the vacuum processes.
The
Hope this
last
can relate to
question.
your answer.
The
Yeah.
last question is there. How vacuum quality affects the adhesion of thin films on substrate?
Yeah, it affects quite a lot, because vacuum is something which controls all the processes, because overall contamination, and in different process the input conditions are different. And vacuum, we saw like very important role. So let me just show again one by one. So in PVD process, we have seen that it uses resistive heating, and it creates the vacuum. So if the vacuum is not there in this PVD process, what happens that there will be more residual gases, and the film quality will not be that great. So you will have more oxides. Suppose you are growing aluminium, so you will see some aluminium oxide as well. In sputtering, the vacuum maintain the plasma and the target material when it grows to that. So vacuum affected 2 ways: plasma inconsistency and the mean free path. So it will affect in the film quality in the sputtering. Now next come to the CVD technique. In the CVD, we have the reaction chamber, and one side we release the plasma and maintain the vacuum. So if the vacuum is not proper, then the gaseous, it will affect the gaseous reaction, and the absence of that gaseous reaction will affect the film quality, because the chemicals cannot properly react, and the inconsistent plasma in case of PCVD will will affect the film growth, because in final film material will have the constituents of other dust particles. Now come back to the ion implantation. In the ion implantation, the beam deflection is everything in the ion implantation. The beam energy, what is released and it reaches to the sample stage, it should be the same value. Suppose you are doing, suppose your input condition says that you need an ion implantation at 2 kilo electron volt ion dose. So if the vacuum is not properly maintained, it may happen that the energy it releases from the ion source and reaches to the sample stage will be a lot different. So it will affect the film quality. And next is the plasma etching. In the plasma etching technique, we uses high level of precision in material removal. It uses the plasma composition and energy and the exposure time. Vacuum affect the plasma composition and the energy input to remove the material. So it will have the improper condition in the absence of the vacuum. So if there is an improper vacuum, overall etching will not be proper. So vacuum ensure that the environment remain contaminant free, and then different input conditions, they are properly being maintained so that you get your desired output. So that's how if vacuum plays important role in these semiconductor processes, and these are being used in all the semiconductor devices.
Thank you so much, Dr. Vinay. We have received a feedback from many of the participants that the session was very informative and they have really learned many new things from this session. I would appreciate your effort and your time you have taken out from your schedule, and that too early morning, starting of your day, I would say. So
No,
I
yeah,
know,
I really appreciate your and thanks for your kind words. And it's really an honor. And in the future, if something comes up, please feel free. I would be very happy to
right, right.
participate
We
and
will be
interact with
planning
the
some
people.
few more such sessions for the participants, and we will try to
Mhm.
collaborate in various other future opportunities, right? So,
Yes.
Ishika, you can take it forward. I know many participants are still having few questions, but time is running short. So, Ishika, you can please take it forward.
Sure, ma'am. A sincere thank you to Sir for such an insightful session on vacuum measurement and control. Your explanation of vacuum measurement techniques, pressure regulations, and control mechanisms has provided practical insights into optimizing semiconductor fabrication. Additionally, your detailed discussion on vacuum pumps helped us understand their critical role in semiconductor manufacturing. We deeply appreciate your time and expertise, sir. Thank you so much, sir.
Thank you, Shika. Thanks. Thank you, everyone. Thanks.
Thank you so much, sir. Have a good day. Bye bye.
Yeah.
Dr.
Yeah.
Vinay.
I'll still be connected till the end of the session. Yeah.
Yes, yes, yes. So the participants, the feedback form is shared with you. You can please fill the feedback form, and we will be meeting tomorrow, the last day, but not the end. We will say we will collaborate further. We have now got various ideas to work and collaborate. So let's start. This is just the starting point. So good night, everyone. Have a good sleep. Thank you. Let's meet tomorrow.